Okay, for what we have in chapter 5, starting off, okay, we're looking at vector length and unit vectors. And we have, by definition, okay, we have the length or norm of a vector, and Rn is going to be where we have what is also referred to as the magnitude of v, and that's going to be equal to the square root or the sum of the squares of the components, okay, that make up this vector. And the length of a vector, if it is equal to 1, it is referred to as a unit vector. And for a unit vector in the direction of v, okay, if v is a non-zero vector in Rn, then the vector u is equal to the vector v divided by its length or its magnitude. It's going to have the length of 1 and will be heading in the same direction as v. And again, that vector u is referred to as the unit vector in the direction of v. And looking at what we have as a set of examples, okay, we have, first of all, it says to find the length of each vector and then find a unit vector in the same direction. Okay, so we have vector v consisting of 3 and 4. Now for the length, okay, you're looking at the length or the magnitude is equal to the square root of the sum of the squares, which we have with the squares of 3 and 4. 3 squared is 9, 4 squared is 16, 9 plus 16 is 25, and the square root of 25 is equal to 5. Okay, so for the length of this vector, that is going to be at 5. And for what we have for a unit vector that is heading in the same direction as v, again, we have the components 3 and 4, and if I divide by the magnitude 5, and the 3 and 4 over 5 we have for the unit vector, you have 3/5 and 4/5. And again, if I took the length of this unit vector, I would be squaring 3/5 and 4/5, which I would have respectively at 9/25 and 16/25. And if I were to add these squares together, I would come out to 25/25, which is 1, and the square root of 1 would be at 1. All right, and let's say that if we have in R3, let's say we have a vector consisting of the numbers 1, 2, and 3. And for the length of this vector, if I take the sum of the squares of 1, 2, and 3, okay, I'm going to have, putting together, okay, we have 14. So the magnitude or the length of this vector is going to be, in exact terms, the square root of 14. And if I'm looking for a unit vector that is heading out in the same direction, okay, so I'm looking at 1, 2, 3, those components divided by the magnitude, which we have in the square root of 14, and without converting, okay, rationalizing the denominator, I would have 1 over the square root of 14, 2 over the square root of 14, 3 over the square root of 14, and rewriting as ratios without any radical in the denominator. Okay, so we have square root of 14 over 14, 2 square root of 14 over 14, and 3 square root of 14 over 14. And in simplified form with the ratio of evens with 2 and 14, the coefficients in the middle, we have 2 square root of 14 over 14 is reducible to the square root of 14 all over 7. Okay, and so it can also be written in this particular form. Okay, now in addition to what we have for length of a vector, as well as what we have, what will constitute a unit vector, we also have what is referred to as the distance between two vectors. And the distance between two vectors u and v and Rn is going to be where we have the distance between u and v is going to be the magnitude or the length of the difference between what we have in the case of u minus v. And let's say that in looking at determining distance, okay, say we have vectors given out, and we have an R2, we have v at 3, -8, and w at 3, 1. And we have in R3, we have x with -104, z with 2, 5, and -2. And first of all, if I look at the distance between v and w, okay, so we're going to have for the distance between v and w, okay, so we have in this case looking for the magnitude. Okay, so for like where I had u minus v, for the distance between u and v, I'm going to have the magnitude of v minus w. And what I'm going to do here is I'm going to subtract 3 from 3, as well as 1 from -8. So you have like your v minus w first coordinates, v minus w second coordinates, 3 minus 3 is 0. Negative 8 minus 1 is negative 9. And the squares we have respectively at 0 and 81. And the square root of 81 is equal to 9. Now for the distance between x and z, okay, so you're looking at, in the pathway, you're looking at x minus z. First coordinates we have negative 1 minus 2. Second we have 0 minus 5. Third we have 4 minus negative 2. And negative 1 minus 2 is negative 3. And the square of negative 3 is 9. 0 minus 5 is negative 5. Its square is going to be 25. 4 minus negative 2 is 6. And the square of 6 comes out to 36. And it turns out that we end up exactly at the square root of 70. Now, for what we have in the case of what is regarded as the dot product, an angle between two vectors. Now we have for dot product, we have for vectors u and v, the dot product is going to be the scalar quantity where we have u dot v is equal to u of 1, v of 1, plus u of 2, v of 2, all the way out to the product of the last elements that we have between u and v, where we had designated u of n, v of n. And for what we have regarding the definition of the angles between two vectors in Rn, and we have the angle theta between two non-zero vectors in Rn can be found by using the following formula, whereupon we had the cosine of theta is equal to the dot product of u and v divided by the product of the lengths of the vectors u and v. And theta is going to be in radians, whereupon we have that 0 is less than or equal to theta is less than or equal to pi. And the radians can also be converted in terms of degrees. And just remark that the author includes, and that is the angle between the 0 vector and another vector is undefined. Now, looking at what we have concerning dot products, okay, and say we have the earlier given vectors v, w, x, and z, and if we're looking at the following dot products, let's say we have the dot product between v and itself, so you're looking at like 3, negative 8, 3, negative 8, and so you have 3 times 3 plus negative 8 times negative 8, so we have the result here is going to be 9 plus 64, which will come out to 73. And if I take the dot product of v and w, so we have 3 times 3, and then we have plus negative 8 from v times 1 from w, and so we got 9 minus 8, so this dot product ends up at 1. And if I take the dot product between w and itself, so you're looking at 3 times 3 plus 1 times 1, and this will convert to 9 plus 1, which is 10. And for the dot product between x and itself, we have, again, negative 1 times negative 1 plus 0 times 0 plus 4 times 4, and the sum of the products will end up at 17. And if I have like z in the dot product with itself, okay, so you got 2 times 2 plus 5 times 5 plus negative 2 times negative 2, and that is going to come out to 33. All right, and now where angle is concerned, and let's say that if you have given, okay, say you have v at 3, negative 8, w at 3, 1, x still at negative 1, 0, 4, and z at 2, 5, negative 2. And let's say we have additional terms or additional vectors in A, where we had defined in trigonometric terms, where A, we're going to have cosine of pi over 4 and the sine of pi over 4. B, we had the cosine of negative 3/4 of pi and the sine of negative 3/4 of pi. And if we're looking at the angle, say, between V and W, now again, we have, in this case, you have the cosine of theta is equal to the dot product of V and W divided by the product of the magnitudes of V and W. So again, you got the dot product of V and W, again, which earlier we had determined to be at 1. Now the magnitude of V is going to be the square root of 73. So you're taking the sum of the squares of 3 and negative 8. And for the magnitude of W, they got the square of 3 plus the square of 1. Square root of that comes out to the square root of 10. And for the cosine of the angle between the vectors V and W, okay, we got, again, the cosine of theta. This will be 1 over the square root of 730. And for theta, okay, you're looking at taking the inverse cosine or arc cosine of what we have for 1 over the square root of 730. And in terms of radians, this will come out to about 1.534 radians. And in terms of degrees, you have about 87.88 degrees. Now, with what we have, say, for x and z. All right. Now, if you notice, we did not get the dot product of x and z, but we're going to. And for what we have in the angle setup, so we've got the cosine of theta is equal to the dot product of x and z divided by the product of their magnitudes. And for the dot product of x and z, so you got -1 times 2. In the middle, we have 0 times 5. And then we have last elements, they have 4 times -2. So you got -2 plus 0 plus -8 or -8. And this will come out to -10. And for the magnitude of x, okay, so you got the sum of the squares of -1, 0, and 4. So we had the square root of 17. For the length or the magnitude of z, so we're taking the sum of the squares of 2, 5, and -2, and that is going to come out to the square root of 33. And for the angle setup, so we got the dot product at -10, and for the product of the magnitudes that we have for x and z, we have what will be the square root of 561. And for theta, you're looking at the inverse cosine of what is going to be -10 over the square root of 561. And so we have about 2.007 radians, or about 114.97 degrees. Okay, and so we got for this one. Okay, so if I'm looking at the inverse cosine, okay, so I'm double checking here, and in fact, let's see, for that figure, okay, so I have what's going to be -10. Okay, so I got -10 over the square root of 561, and I'm double checking, and again, the inverse cosine, yep, 2.007 radians, or about 114.97 degrees. Okay, now looking at what we have for the vectors a and b, where we have expressed in terms of cosines and sines of angles for the coordinates. And I was going to mention for that dot product, this is going to be reminiscent of the sum and difference formulas from Math 172. And in fact, you have like your cosine alpha, cosine beta plus sine alpha, sine beta. That would be equal to the cosine of alpha minus beta. And like your alpha would be pi over 4, beta would be -pi over 6, and pi over 4 minus -pi over 6, that would be the cosine of 5/12 of pi. But if I were to fill in the values, like cosine of pi over 4, square root of 2 over 2, cosine of -pi over 6 would be like the square root of 3 over 2, and here we have sine of pi over 4 is the square root of 2 over 2, sine of -pi over 6 would be -1/2, and so the dot product would come out to this difference for what we have in exact terms. And for what we have for the magnitudes of a and b, okay, we had the sum of the squares of cosine and sine at the same angle, and those sums will both come out to 1. And so the cosine of theta, that's going to be equal to what we have in the dot product, since the magnitudes of a and b are each at 1, and the product being at 1. And for theta, we're looking at the inverse cosine of the difference between the square root of 6 and the square root of 2 all over 4, and this comes out to right at 1.309 radians, but it does come out exactly to 75 degrees. Now, for what we have in the case of orthogonal vectors, now two vectors u and v will be said to be orthogonal whenever the dot product is equal to 0. And it says here, even though the angle between the 0 vector and another vector is not defined, it is convenient to extend the definition of orthogonality to include the 0 vector. In other words, the vector 0 is said to be orthogonal to every vector. Now, regarding parallel vectors, now two non-zero vectors, u and v, in Rn are parallel when one is a scalar multiple of the other. That is, where we have u is equal to the scalar c times v. Moreover, if c is greater than 0, then u and v have the same direction, and if c is negative, then u and v have the opposite directions, or are heading in the opposite direction. The next theorem gives a formula for finding the length of a scalar multiple of a vector. Okay, and for what we have looking at examples, okay, so if we're looking at determining whether the following vectors are orthogonal, parallel, or neither. And let's say that if we have u to consist of -2, 5, 3, 2, v consisting of -2, -3, 3, and 1. And looking at whether they are orthogonal, to be orthogonal, the dot product must be 0. So we got -2 times -2 plus 5 times -3 plus 3 times 3. And with the last components, we have 2 times 1. And it's going to turn out that the dot product is equal to 0. So right away, these vectors will be orthogonal to each other. Now, let's say if we have another pairing. Okay, so we have u consisting of 4, 6, -6, -2, v consisting of -2, -3, 3, and 1. Now, the dot product for this set, okay, is going to be -46, which does not equal to 0. So we cannot say that this pair will be orthogonal. But to see if we have them to be parallel, well, it must be that one vector has to be a scalar multiple of the other. And if you notice, okay, like v consists of -2 for the first element, u consists of 4, and like -2 would go into 4 -2 times. And let's say that, okay, now for u, you got 4, 6, -6, -2, and this would be -2 times -2, -3, 3, and 1, which happens to also be v. So we have equal to -2v. And so u is a scalar multiple of v. In this case, this set is going to be parallel. And if I had u to consist of +2 as opposed to -2 at the end, guess what? The dot product is still non-zero, so they're not going to be orthogonal. And guess what? What I have for u is not going to be a scalar multiple of v. And so in this case, you're going to have neither orthogonal nor parallel. All right. Now, for the case of finding orthogonal vectors, and say if we have, as an example, say if we are looking at determining all vectors in R2 that are orthogonal to u is equal to 4 and 2. And if we let v be equal to v of 1, v sub 1, v sub 2 be that which is orthogonal to u, where now the dot product is going to be 0. And so for what we got with u at 4, 2, okay, and for the dot product, we have 4v1 plus 2v2 is equal to 0, which implies that if we write v of 2 in terms of v of 1, so we got 2 v sub 2 is equal to -4 v sub 1, and simplifying, we had that v sub 2 is equal to -2 v sub 1. So every vector that is orthogonal to 4, 2 is going to be of the form where if we have v sub 1 is equal to t, we're going to have that v sub 2 is equal to -2t. And you can also write this in multiple terms. We have t times 1 and -2, where upon t is going to be a real number. And let's say that if we were to determine all vectors in R2 orthogonal to u is equal to -7, 3. And if we let v be orthogonal to u, so again, we got the dot product between u and v is equal to 0. And so we have u at -7 and 3, v at v sub 1, v sub 2 equal to 0. And so we got with the dot products, we have -7 v sub 1 plus 3 v sub 2 is equal to 0. And so isolating 3 times v sub 2, okay, that is going to be equal to 7 v sub 1. And solving for v sub 2, we have 7/3 v sub 1. And so for v, again, we have equal to v sub 1, v sub 2. And so that is equal to v sub 1, 7/3 of v sub 1. And letting v of 1 be equal to t, well, it turns out that v sub 2 is going to be equal to 7/3 of t. And so that will be the orthogonal vector in this case. And if I were to determine all vectors in R3 orthogonal to u is equal to -1, 4, and 7. And again, letting v be orthogonal to u. So we have u dot v is equal to 0. And upon substituting, okay, so we have -1, 4, 7 for u, v sub 1, v sub 2, v sub 3 for v. Again, the dot product is equal to 0. And so we got negative v sub 1 plus 4v sub 2 plus 7v sub 3 is equal to 0. And if I isolate the highest subscripted term in this case, which is 7v sub 3, I'm going to have this equal to v sub 1 minus 4v sub 2. And in this case, we're going to have v sub 3 is equal to 1/7 of v sub 1 minus 4/7 of v sub 2. And just putting it all together. So as I'm increasing the numerical subscript values, I'm kind of going in opposite direction alphabetically. Okay. In other words, moving forward in ascending order with the numbers, but I'm going in reverse alphabetical order. So if I let v sub 1 be equal to t and v sub 2 be equal to s, okay, now v sub 3, so I have 1/7 of v sub 1, so that's going to be 1/7 of t, and minus 4/7 of v sub 2, so that's going to be minus 4/7 of s, and that will be the resulting orthogonal vector. Okay, now if I determine all vectors in R3 orthogonal to u is equal to 2, -1, 1, once again letting v be orthogonal to u, and so we have with the dot product, okay, have u dot v is equal to 0, and filling in, so for u again, I got 2, -1, 1, v I have v sub 1, v sub 2, v sub 3 is equal to 0, and we have with the dot product, so you got 2 times v sub 1 minus v sub 2 plus v sub 3 is equal to 0, and upon isolating v sub 3, so that's going to be equal to -2 v sub 1 plus v sub 2, and again, just like going the reverse route, as I increase the subscripted values, I want to take the reverse alphabetical order route, so letting v sub 1 be at t, v sub 2 be at s, it's going to turn out that for the orthogonal vector, that is going to be t, s, and for v sub 3, that is going to be -2t plus s.